So before we get into talking about the chemistry of aldehydes and ketones, as usual, I want to just give a couple of examples of important molecules that incorporate these functionalities so that we can understand why these functional groups are important. So we'll start with aldehydes. So this is a generic example of an aldehyde. Basically what we have is a carbonyl with substituents, one of which is going to be a hydrogen and the other of which is an organic group, except in one special case, formaldehyde, in which case both of the substituents are hydrogens. So formaldehyde is the simplest possible aldehyde, and really it's the simplest possible carbonyl. You probably know formaldehyde from its use in basically preserving biological specimens from even all the way back to high school chemistry labs. But it's also used as an industrial chemical as well to make plywood and a variety of other things. There are obviously a very wide range of possible aldehyde structures. Just in terms of nomenclature, again, you don't have to memorize the nomenclature, but I do want you to recognize it when you see it. So in some cases, we're going to see things named as something aldehyde in the name. So this is acetaldehyde. Its proper name might more appropriately be ethanal with an al at the end, but this one is so common. It's called acetaldehyde. It's sort of a derivative of acetic acid, if you will. Benzaldehyde is another one that you'll see quite commonly. So this is a benzene ring with an aldehyde coming off. But in general, what you're going to see is structures with an al at the name. So this is an aldehyde. Again, it's commonly called butyraldehyde, but you will oftentimes also see it called butanal, and you'll see other more longer structures with the al at the end of the name, and that means aldehyde. Okay, so where do we see aldehydes? Well, many smaller aldehydes are going to be components of good smelling or good tasting compounds. One of the common ones is octanal. So this is just a simple straight chain 8-carbon aldehyde, and this has actually a very pleasant smell, which has been described as lemony or akin to roses, or even a fatty odor, which I guess is meant in a good way, and I'm not quite sure what that means. But in general, octanal has a very good smell. It's found naturally in citrus oils, and it's very much used in perfumes. Cinnamaldehyde is one that you're surely familiar with in smell and flavor, if not in structure. This is the structure of cinnamaldehyde. It's actually pretty widely used for research in organic chemistry, and it is the component that's responsible for the flavor and smell of cinnamon. And I can tell you firsthand that whenever you open a bottle of cinnamaldehyde, you're absolutely infused with the smell of cinnamon. And in fact, the essential oil that comes from cinnamon bark is almost pure cinnamaldehyde. Another one, and we've talked about this one, common aldehyde that I think everyone is familiar with, is vanillin. Right? So here's the structure of vanillin, and it's again the major component of both the flavor and the smell of vanilla. Everyone has vanilla products; they're very common. And you've probably smelled the vanilla extract that you get. Now, there's two different kinds, one of which is synthetic. It's made in the lab, and the other, which is more expensive, is actually extracted from the vanilla bean. If you ever have the chance to smell the vanilla bean itself, I highly recommend it. It is absolutely intoxicating, and you wouldn't think it would be so different from the extract, but it is a completely different experience entirely, and I think that if heaven has a smell, it's probably the vanilla bean. Okay, well, here's a food product or food that's a lot more controversial than those other three. I don't know many people who hate the taste of vanilla, but cilantro is a lot more polarizing. So many people like like cilantro. People will describe it as having a fresh taste, zesty, citrusy. Personally, I find it quite agreeable. I love it in guacamole. But others have a much worse reaction to it. So they really find it quite revolting. And I would recommend this article in the New York Times if you're interested. It talks a little bit about this polarization among foodies. Some great quotes about people who hate cilantro. So this one's from Julia Child, and she says that cilantro and arugula, she doesn't like them at all, and they have kind of a dead taste, whatever that means exactly. The Oxford Companion to Food actually says that the aroma of cilantro has been compared with the smell of bug-infested bedclothes. So that doesn't sound quite very appealing to me. And many people will describe the taste of cilantro as tasting like soap or even tasting like bugs. How they know that, I don't know. But obviously none of these are describing something that most people would want to eat. So what is going on here? Some people like cilantro, other people obviously absolutely hate it. Well, the flavor of cilantro comes from probably about half a dozen chemicals, and a number of them actually turn out to be these long straight chain aldehydes with a reasonably similar structure. And so it turns out that these aldehydes are actually derived from fatty acids. So they have these long greasy chains, and then in these cases they have the aldehyde at the end. And it turns out that these exact same aldehydes are oftentimes used in soaps. So they actually are soap molecules. And in fact, they are also made by certain insects, either as to attract mates or to ward off predators. So it literally is the exact same chemicals that are used in soaps and by insects that are in cilantro. So a better question is not why do many people hate cilantro, it's how in the world do those of us who like cilantro, how can we even stand these flavors? And that's probably gets more into neuroscience than chemistry. But there you have it. Enjoy your next bowl of guacamole, and you're welcome. Here's one that I think is probably less controversial. So this is a wonderful molecule called oleocanthal, and it's actually a principal component, particularly in extra virgin olive oil. So if you've ever had extra virgin olive oil and you have that burning sensation in the back of your throat, oleocanthal is responsible for that. Right? So it is especially present in extra virgin olive oil that hasn't been processed. You'll find a lot less of it if you get if it's not extra virgin. But what's interesting about oleocanthal, in addition to that actual flavor and burning sensation, it has actually been shown to have potent anti-inflammatory properties, very similar to other types of anti-inflammatories like ibuprofen. So it actually can be a pain reliever if taken in significant quantities. Now, most people probably wouldn't drink or eat the amount that you would need to get that effect, but it's they might, and it turns out that olive oil appears to be actually quite healthy for you. So it's one of the good fats, and so you can go nuts. Of course, there's a lot of calories in it. So that's the trade-off. But what's maybe even more interesting is that there's some evidence to suggest that oleocanthal may be useful in preventing heart disease, which may be one of the characteristics responsible for the benefits of the Mediterranean diet. It might also have some use in terms of warding off Alzheimer's. And then most interestingly is oleocanthal has been shown to have anti-cancer properties. And so I point you to this article here, or you can Google it. It turns out that oleocanthal very rapidly kills cancer cells. So I don't know in terms of how that translates to human biology. I don't think the issue is settled, but it certainly is interesting and gives us all, I think, all the more reason to keep eating our Mediterranean diet foods. Okay, so ketones. Ketones are very similar to aldehydes. In this case, rather than having one hydrogen substituent and one alkyl, in the case of ketones, they're just two alkyl substituents. Okay, so the simplest possible ketone is acetone. It's probably something you've heard of. This is actually widely used as a solvent in chemistry, and it's also the component in most fingernail polish removers. And so that actually would just dissolve the fingernail polish. It's also used to make the bisphenol A polymer. So we talked about that briefly in the aromatic section. Interestingly, you can make derivatives of acetone. So dihydroxyacetone is a naturally occurring compound, but it's used in a lot of sunless tanning products. Right? So if you rub dihydroxyacetone on your skin, you'll get basically a fake tan, which can certainly go wrong. Many of these products will create an orange tan instead of the brown that people are going for, but they figured out ways to use this chemical to get a reasonably good effect. As we talked about with ethers, whenever you have two organic substituents around a functional group, you have this potential to make cyclic versions, okay? And so ketones can exist in rings. Like the ketone functionality itself can be part of the ring. And one of the most important cyclic ketones is cyclohexanone, right? So it's just a 6-membered ketone. And the reason that this is important economically is that it's used to make the polymer nylon. And so cyclohexanone is produced on a billions of kilogram scale every year. Another cyclic ketone, you might have learned about this last year when you learned about stereochemistry and enantiomers, is carvone, right? So here I show carvone. It has one stereocenter, and so it's possible that it can exist in 2 different enantiomers, right? There's R-carvone and S-carvone. The only difference between these two is simply that they're mirror images of one another that are non-superimposable, okay? So just that stereocenter has been changed, otherwise they're exactly structurally the same. But in terms of our perception of these compounds, R-carvone smells like spearmint, and S-carvone smells like caraway seeds. So those are 2 drastically different smells I'm sure you've come across them. And so that the only difference there again is just that they're mirror images of each other. And that basically just has to do with how these molecules are interacting with the receptors in our nose. You can have other types of cyclic ketones, so very large rings. This is an example of a large, I believe it's a 15-membered ketone called muscone, right? So it's just a big ring, and then it's got a stereocenter, and then there's the ketone. And this actually turns out to be naturally produced. It's a secretion of the glands of the musk deer. And so this is a picture of a certain species of musk deer. What's sort of bizarre about these guys is that they have fangs, right? So it looks like Bambi is dressing up as a vampire or something. But these deer produce this molecule in their glands, and so muscone has this characteristic scent that we call musk. And so muscone is actually very oftentimes used in perfumes. But since musk deer are actually endangered, most of the muscone that's used in perfumes is actually synthetically derived rather than naturally. And the final ketone that I'll tell you about is a personal favorite. It's curcumin. This is an example of a 1,3-diketones. There's 2 ketone functionalities in this molecule. Curcumin is the principal component in turmeric. Right? So this is the ground root turmeric, and this is this bright yellow spice that's used in curry. You find it very often in Indian food and Thai food and other types of Asian food, but you also see it in very many products. One of the most common is mustard. So if you ever just put yellow mustard on a hot dog, the thing that gives that its bright yellow color is actually curcumin. And it has a reasonably pleasant flavor. It's very spicy, so it basically has the flavor of curry. What's interesting, in addition to its culinary uses, is that curcumin also has pretty potent anti-inflammatory properties. And so instead of taking, say, ibuprofen after a long run or a hard workout, you might consider taking curcumin in tea form. It's something that I do on occasion, and it's a reasonably pleasant tea, but very unusual. And I can verify that a strong cup of turmeric tea actually does have sort of that pain relieving properties that you would expect from other pain relievers. But perhaps even more intriguing, although less established, is the fact that curcumin might also have some interesting biological activities such as anti-cancer or possibly neuroprotective properties. So I think the jury is very much still out on that, and this would fall into the category of folk medicine. But again, I think you know, if nothing else, it's more ammunition to keep eating some of these wonderful cuisines that we find in Asia. Okay, so that's some aldehydes and ketones that we see in our everyday world. What we'll move on to now is talking about the chemistry of these functional groups.